Hi, in this tutorial we will study eigenspace representation of images. So what we want to do in this topic is to have an image that can be represented as a linear combination of other images, and in this case all images are faces. So we will see that an image is in this topic we want to consider to be a square matrix, that means the same number of columns and the same number of rows, and this to be a point in an n by n dimensional or n square dimensional space. And for this we're going to have eigenfaces, in which in this case the notation is going to be the e1, e2, and so on up to em. So we're going to have m eigenfaces, and these or eigenvectors, and these will define a basis set like we have in the previous tutorial. And so the each phase will be defined in terms of how similar is to the basic images, or what we can say is that what we want is that the image I can be represented as a linear combination. So look at what we have here. So we got an I, which is the image, and then this image is being represented as a linear combination of these eigenfaces or eigenvectors. So e1, e2, en, these are the eigenfaces. So we got that addition, but look at that, they are being multiplied by the scalar w, which is a weight. So the idea is that every image that we're gonna have in the data set is gonna be represented by the same type of linear combination, in which what is gonna be changing is the W1 and W2, the weights. So then we can relate each image with the weights. So and then this can maybe seen as some type of vector or index over the image that somehow is the characteristic of that image I. So let's start with the idea of this algorithm. So first, what we will do is we have to compute the average image A from all training images. So in this case, we got all the images from a given set, and then you see is a basic averaging procedure. We add in the images, and then we divide by the total number of images, which is m, and then we get a new um, face. And this is an interesting experiment, because remember, these are all faces. So we're averaging all those images into and creating another one, which in this case is A, so it's the average face of the human. So look how interesting is this concept that we have, like, well, not the average face of the human, but the average human face of this set. So we have a particular set of faces, and then we compute that, the A. And then what we will do, you see here, is kind of computing the weight is some type of similarity with respect with each of the images with respect with the average. So you see here this expression. What we have here is the input image that we're comparing minus the average, and then we do the multiplication in this case with the AK eigenvector, and then we got a weight. So and this sometimes, so this gives some type of similarity or a number that says how similar is this with respect to the which each one of the eigenvectors. And then what we got on 3 is that we got that W's that somehow is the weight in which is kind of related with each one of the eigenvectors or eigenfaces. So you see, this is really interesting, because now we got that W, and these are all the weights of all the similarity measures of that face with respect with the other faces. So up to here, this is kind of the general idea that each one of the eigenfaces somehow makes a contribution to the face of the image, and then by that linear combination. So now once we identify the W1 and W2s, and we got that representation of faces using eigenvectors or eigenfaces, Then we will have a face recognition algorithm. Then the face recognition is basically 4 steps. So from the training set of the face images, what we need to do is compute the largest eigenvectors. And computing eigenvectors is another topic related with linear algebra and, um, and matrices. So we will explain that later. And or in this case also we call in the eigenfaces. And for each different person in the set, what we want to compute is the W, which is the weights associated with in the linear combination. And then once we have a test image, we projected that and we compute that W test. And the face recognition, the last step is once we have, so each of the faces in the data set had an associated W. Now even the test image, the one that we're going to compare with the other image, has an associated um, W. So then what we need to do is to compute the distance to kind of specify some type of similarity between the images, and then we can rank a result and say, okay, this image, the test image, is more similar to this one in the data set. So that's the main idea of the algorithm. We're going to have some additional readings for this. This is a quick example in which we said, okay, let's suppose that we have images that are 3 by 3, and then we got m is 2 images, and then we're going to assume that m prime is 1. That means there was just one, selected one eigenvector as the largest eigenvector in the set. And then the representation in this notation, so you see, we see the image as a square matrix, right? But then it's represented either as a column or row vector. You see I sub 1 and I sub 1 t, the transpose. These all three are the same representation of that I1. So I1 is, you see, 0, 0. So now it's represented like a one-dimensional array in this, like a column, or in this way, so we can actually have the matrix multiplication when, for example, between the transpose and the column and the row. So so here the average of the matrix, that should be easy to see the average in this case. You add 0 plus 0, and then gives you the 0, and then this element 0 plus 10, it gives you the 5, and then you can continue checking the numbers when you are basically adding the numbers from those two matrices and then divide it by 2. So this is the I sub 1 is the eigenvector. I just was putting the values of the average, and that was right. Okay, then as we say here, you subtract from each image the average, and then you do the multiplication with the eigenvector. So in this case, here is the computation. This is the AT. This is an example. The image transpose minus the average. That will be the result. And then once we do the multiplication between this and the eigenvector, which is this number, so 5 times 0 will give you 0, 0 times negative 5, 0. So there are only two numbers that comes from that multiplication. I think it's 10 with this 5. So I get 250s. So the W1 is 100. And then if we do that for the other image, so this is the average, and this is subtracting the image minus the again, one is the eigenvector, and then the other is the subtraction of the image, like it says here, minus the average, and we do the multiplication, and then we get a negative 100. So let's suppose that I have now, I'm done with my training set. So my training set has two images. One of those has a W1, which is 100, and then the other is negative 100. And then let's say that we have an input image, which this is the data, and then for that we follow the same procedure in which we multiply by the eigenvector, and then these numbers we subtract from the average, right? And then we do the multiplication here, and then we get a 15. So once we have the weights, Then I can compare that with each one of the other images, and then I can rank the results. And once I rank the results of comparing of the the multiplication of those and say which one, then I can rank the results and decide that I1 is the most similar. Then I have another example here. Well, here is the selection of the eigenfaces. It says that for each training image, this will be the procedure to for the selection. This is again the for each image we subtract the average, and then from that we compute what we call the covariance. And then once we have that C, we follow another procedure to find the eigenvectors. So for all of that, we can just use Scilab and provide metrics and says that we can get the eigenvectors that are associated with that. And then we want the ones with the largest eigenvalues, and this is the one that will be my eigenfaces. Okay, so this is one of the procedures. So we're just gonna rely on some software. Maybe again we got some software to compute the covariance. We have some software also inside lab already, some functions to compute the average phase, and then we also have some to compute the eigenvectors. So we just need to understand that this is what is happening, and this is just another example in which we say, let's assume that I have an image database, and I have in this case 4 images, and these are the W's associated with each image. And then I have an input image. These are 2 input images, which is Q1 and Q2. And then I want to compare and find some type of similarity. So what I can do is do the dot product Q1 W1, or some type of distance or some type of comparison. And then what you do is you multiply each element 0.6 times 0.6. That's how you get the 0.036. Negative 0.1, negative 0.1, positive 0.081, 0.1, and so on. And then you add those numbers, you get those numbers there, and then you compare, and you have a way of rank the results in this case. So if you're computing Q1 with the other images, and it says that these are the results in ranked. So haven't done the one for Q2, but maybe that will be a good exercise for you to practice.